Hi everyone. Thank you all for being here. Like he said, my presentation is on line of sight on cloud-optimized GeoTIFFs in CesiumJS. I'm Cameron Woodbury. I'm a 3D front-end engineer for Hobu, Inc. I know at least some people here know Hobu, Howard of Hobu. I'm based out of Minnesota, but Hobu's based out of Iowa, and I've been with Hobu for about 3 years. We are an open source software engineering company. We've been around for quite a long time, and we are primarily known for PDAL, but we are also very active with GDAL and Proj and other technologies that enable us to do what we do. My main thing at Hobu is Eptium, which is our Cesium and React library for point cloud rendering. The way that we got to Cesium was actually trying to build just a self-built renderer for point cloud files in the browser. And we decided we didn't want to self-build anymore, so we moved on to Poetry, which some people here may have heard of. And then from there, that didn't quite fit with everything that we wanted, especially the geospatial context for the point clouds to see where they're at. And so that's where we finally found Cesium. And we chose Cesium to take advantage of the amazing renderer and ecosystem. And we chose React on top of that for the developer experience, at least for our Hobu developers, and state management. And I will be referring to Eptium throughout this presentation, but pretty much everything does apply to CesiumJS, sometimes even nicer without React in the way. And some of Eptium's features include COPSI and COG rendering, so cloud-optimized point clouds and GeoTIFFs, shareable save states, which I have taken advantage of throughout the presentation with QR codes up in the corners. So if you see a screenshot on a slide and a QR code, you can scan that code to pull up our viewer right with that data in the screenshot. And then the focus of today's talk will be on Eptium's viewshed analysis features. Here's a general overview of the topics I'm going to cover today. Go into some background information on cloud-optimized GeoTIFFs and point clouds, and then how we actually use cloud-optimized GeoTIFFs in Eptium. Do an overview of what line-of-sight analysis is, and then some details about the actual functionality for line-of-sight that we have in Eptium. And then I will finish with a 2-minute video demonstration. But first, the background information on what we call cloud-optimized resources, specifically meaning COPSI and COG, point clouds and GeoTIFFs. And these are extensions of legacy geospatial formats. So COPSI is just a special LAZ 1.4 file, and COGs are just special GeoTIFF files. And they're special because they're optimized for bulk transmission and incremental access. The data is structured in addressable chunks, which takes advantage of HTTP range requests to just grab the parts of file that you need, the incremental access. And as I mentioned, Eptium was created specifically for rendering COPSI files directly in CesiumJS. And since joining Hobu about 3 years ago, my personal focus has been on improving the COG support, the GeoTIFF side, the raster presentation. And the actual specific details of COPSI and COG aren't particularly important for this talk today, but I will explain some benefits and drawbacks for why we've chosen this. Cloud-optimized resources are great for browser-based GIS applications. And some of the reasons that we chose it is because of the wide software support. Due to being legacy-compatible formats, we get to take advantage of the whole ecosystem around GeoTIFFs and point clouds, namely Goodle and Poodle. And these files come with a gradient of capability, so you get to opt in to just the capability that you need, be it the range requests or spatial indices. And they are very convenient for bulk transfer and federation because they are structured for organizational benefits. There's no need to shred the data up for storage or organizing it, making it a lot easier to copy and move like from server to server or server to local. But just like any decision, it's not a perfect solution. There are trade-offs when choosing between file types, and there is no perfect solution for visualizing, organizing, and analysis all at once. And these file formats do have an intricate design to accommodate older behaviors and usages of LAZ or GeoTIFF files. And so that brings with it some legacy complexity and sometimes performance limitations. But now I can get into how we're actually using cloud-optimized GeoTIFFs in Cesium, in Eptium. But first, it wouldn't be possible without GeoTIFF.js. GeoTIFF.js is a JavaScript library for reading and writing GeoTIFF raster data from remote or local sources. It works in both the browser and Node.js. And it powers not only our viewshed analysis, which I'll get into, but we also found that it's used for cog imagery, and we use it for cog terrain. Yes, because Eptium is able to render cogs just dropped into the viewer or given as a URL directly in Cesium. And we found this open source package, TIFF Imagery Provider, which implements the Cesium Imagery Provider class right over top of the GeoTIFF.js source data. And this package is great. It supports all kinds of features that we need, like reprojection and resampling of pretty much arbitrary cogs, multi-band RGB rendering, and single-band rendering with a custom color map or a bunch of built-in color maps, and a bunch of other customization options. And Eptium includes convenience features and popular color ramps like Viridis for rendering, but it's otherwise just using the open source package. You can go and get it off of GitHub or NPM right now. And TIFF Imagery Provider is also used to render the viewshed data once we've computed it, because it is exported as a raster also. So here we're finally on to one of my favorite Eptium features, the ability to render cog digital elevation models as quantized mesh terrain tiles on the fly in the browser. So this is originally based on the open source Cesium Martini package, which uses Mapbox's Martini algorithm on their terrain RGB data to quickly create right triangulated irregular network meshes, or RTIN meshes. And RTIN meshes consist of only right-angled triangles, which makes them less precise than traditional Delaunay-based tin meshes, but they are much quicker to compute. And that increased speed enables us to just drop a raster in the browser. It'll fetch all the data from the raster, all the source elevation data, and compute a quantized mesh terrain tile right there in the browser for you. And say it's based on Cesium Martini because we did adapt it to work with arbitrary rasters and coordinate systems, which is not something that we've open sourced at this moment, but it is available in Eptium or in the Eptium viewer for you to use with any of your own cog data. Now finally, I'm on to the thing that everyone came here for today because it was in the title, the line of sight features. But first, it's important to distinguish what I mean when I'm talking about line of sight or viewshed, because they are separate things, but they're interconnected. And I've shown a two-dimensional cross-section of each concept. So the line of sight on the left is essentially an imaginary line between 2 points in 3D space. If that line is unobstructed, the target point is considered visible from the observer point. Whereas if there is an obstruction, like a building mesh or like vegetation, just something in the way, then that denotes that the object or the target point is not visible from the observer. And some implementations do track multiple obstructions by just following the line all the way through. And this would be easy to do with Cesium's drill picking, but that's not something I've investigated yet. And yes, a line of sight is different from a viewshed in that a viewshed is composed of line of sights. It's essentially mapping the line of sight from the observer to every single target point within range. So you can imagine drawing that same sight line to every single raster cell in your raster. And typically this is done with raster source data or TIN data and a viewshed algorithm to avoid calculating potentially billions of sight lines if you're using billions of raster cells. But why do we do viewshed analysis? The primary question answered by viewshed analysis or line of sight analysis is what can I see from here and or who can see me? And so a few of the applications of viewshed analysis includes wireless communications, like seeing if radio or cell towers can communicate with each other, and satellite communication, and urban planning, so building construction or attraction visibility, defense and military operations, and even NASA mission planning, such as the Mars Exploration Rover, where they did viewsheds of the craters and landing sites to locate which ones would be most suitable. Now that I've covered the what and the why, we can finally get into the how. And the how for our 2D viewshed computation is largely enabled by the COG support that I've touched on. What we do is we found a NASA tool, the MMGIS viewshed tool, which is based on GDAL viewshed, which is kind of the holy grail, at least in my sphere, for viewshed algorithm. And it is based on a paper from 2000. And we took the NASA-based tool, which is just a JavaScript implementation of GDAL viewshed with a few extra options, and adapted it to work with GeoTIFF.js source data. But it's otherwise based on that tool. They just had their own non-GeoTIFF.js version of raster input. And the inputs to the algorithm include the raster elevation data, so your DSM or DTM source cog, the observer's position, and most of the options that are in GDAL viewshed, if you're familiar with that. So observer and target height, maximum distance, and curvature of the Earth. And then the NASA tool also had field of view options, so we've pulled those over as well and got those working in Cesium. And our implementation does work off of and across rasters, which is useful with incomplete or tiled DEM data. And the viewshed is written out as a GeoTIFF raster based on the source, meaning it has the same resolution and CRS as your input raster, and then has the following encoding of 1 for visible positions, 0 for non-visible positions from the observer, and 2 for the observer's original position, so you know where it was computed from. So why is this cool? Largely because of the cloud-optimized formats and the capabilities of the browser and CesiumJS. The implications of our 2D viewshed is that we're able to leave the data where it's at. We don't have to pull it around from server to server. And we can fetch just what we need when we need it. So just the raster tiles at the right level of detail when you're zooming in, but then when you go to do computation, you can actually grab all of the data because of the organization. And this enables in-browser analysis in real time, leveraging the power of CesiumJS to do analysis and export it in common formats for sharing and using externally, such as in GDAL with the raster or QGIS. So here, getting away from the cloud-optimized resources, getting away from the GeoTIFF, we did want raster or visibility data for non-raster resources in the scene, in our Cesium scenes. So this includes 3D tiles, entities, and terrain that's not based on the rasters. And that's when I discovered the scene picking API. So this feature uses scene.pickFromRay to find obstructions between 2 user-defined points in the scene. And it does interact with everything in the scene, including non-raster data. So I've got a couple of models here on top of our terrain data. And for our use case, this is mostly a prototype feature because it doesn't really export anything usable on its own besides screenshots and videos. So here, I've got a quick video showing the point-to-point picking in action, just because I felt it was easier to show than explain. But yeah, so if the point is visible from the observer point that was on the end of the plane, then you get a blue position and a green line. Whereas if your target position, there's obstructions like in the buildings, then it will mark the visible point with the blue and continue the line out with the red. And so yeah, this feature doesn't quite satisfy our requirements for a non-raster viewshed because of the lack of a GIS usable export. But finding this was instrumental in implementing our 3D viewshed. So I mentioned that typically viewshed analysis is done with an algorithm, like with raster or TIN data, to avoid calculating potentially billions of individual sightlines over and over for similar points. And we do have an algorithm for our 3D viewshed that I'll show in a moment. But unfortunately, it does not help us avoid calculating these sightlines potentially billions of times. So how do we get from here to a full 3D viewshed? Sphere packing was my idea. So the Fibonacci lattice shown here is a method for evenly distributing points on a sphere. And so we use this algorithm to generate n rays from the observer position out to the nearest visible point in the scene. And this diagram depicts kind of what the 3D viewshed is scanning for if you imagine the observer at the center of these spheres and then each vertex being a visible point from the ray being projected out from there. And so it looks like this when it's in the cesium scene. So here, this was a 3D viewshed calculated from 20,000 rays. So we had to run that pick from ray most detailed this time 20,000 times to find the nearest visible points in the scene. And the solution can certainly be improved. We investigated TIN viewshed algorithms that could work with the quantized mesh and model and 3D tile mesh data, or a voxel-based approach. But once I found the scene picking and tried it, the speed worked out enough for us, so I haven't dug deeper into those at all. And this solution does work for collecting line-of-sight information with non-raster sources, like entities and 3D tiles, because we're able to collect all of those visible points in Cesium's coordinate system and export a simple Earth-centered, Earth-fixed polygon file format, or PLY, point cloud file. And so here's the promised video demonstration. So we zoom in over my Montreal COG DSM, being rendered as terrain. And then we find a good spot in the middle here and place an observer, which immediately computes and renders the 2D viewshed with default settings. And then I increase the observer height to try to get more visible positions to show in the video, and then show the radius preview increasing as well, just trying to get more green, and then bring up the height. And so here we see with a higher observer, it's able to look down on more of the area. And then here I use the point-to-point line of sight to show that the cesium scene picking generally does agree with the Gödel viewshed algorithm, where the green positions are marked as visible and non-green positions are blocked by somewhere else that is visible. And then here I zoom back out for the 3D viewshed because it depends on the contents of the scene. And so with Cesium's culling of non-visible tiles, you want it to be like showing what you're actually trying to mark as visible. But then here I input 7,500 points for sphere packing and wait a moment for the scene picking to complete. So here it's running that pick from ray most detailed the 7,500 times. And then here it outputs all the point data, so each point that was visible. And then I rotate it around to show that the scene picking still generally agrees with the 2D viewshed. You get lots of green points in the green raster area, and then not really any green points anywhere that the 2D viewshed didn't say should be visible. And then here I show that you can export the 3D viewshed as a PLY file and the 2D viewshed as a GeoTIFF raster. And so here, real quick, I have a bunch of other features that I did not plan on having time to talk about. So we're able to group observers and export an intervisibility viewshed using the 2D viewshed, just stitching them together, calculating differently. Generating random observers within a user-drawn GeoJSON if you're just trying to get kind of a general map. And some of the other 2D viewshed options, and I didn't show off the 3D tiles interoperability. And then pictured is the intervisibility viewshed raster being rendered in QGIS, showing the interoperability of the file formats. And yeah, I think that's about it for time. I do have a quick video showing the GeoJSON drawing, so I'll let that play.
Thank you, Cameron. We don't have time for Q&A, but you can reach him after the session. So please, a big applause for this amazing presentation. Thank you very much, Cameron.